Welcome to another edition of Tales from the Workshop. What I'm going to do today is I'm going to take you through the process of solving for all the missing values for the circuit that we have before you today. It's called a resistive, inductive, and capacitive parallel circuit. I'm going to take you through how is it that we can solve for all these missing values using trigonometry formulas as well as Ohm's law. Now, what we see here is that we have a given voltage of 112 volts, a resistive value of 60 ohms, an inductive value of 85.7 ohms, and finally, a value of capacitive reactance, 75 ohms. Now, these values were chosen very specifically because I have access to a lab volt workstation, and these values correspond with what I can get out of the lab volt equipment. We are going to build this circuit in a subsequent video, so please keep an eye out for that on my YouTube channel. Don't forget to like and subscribe if you enjoy the series. Now, let's get to work. Well, what we can see here is that because this is a parallel circuit, and I'm going to have to go and grab a marker. Because this is a parallel circuit, popular theory is the voltage from the power supply is going to be the same across every branch in this circuit. With 112 volts of applied voltage, it's just a simple matter of writing down 112 volts down this branch, 112 volts down the inductive branch, and finally 112 volts down the capacitive branch. When it comes to filling in the values, it's a simple matter of transposing that number. Now, if you've been watching or following any of my previous videos, I'm kind of predictable, and I will always default to finding the value of impedance. But in this situation, I don't need to. I've got everything I need to start solving for the missing values across each of my branches. And so that's the tact, or how I'm going to approach this today. I'm going to be starting to solve for all the missing values across my resistor branch, namely the value of current, and with that will lead me into calculating for the value of power. And then I will continue on for each branch. So grab yourself a pencil, a sheet of paper, don't forget a scientific calculator, and follow me along. Our first operation consists of trying to find the value of current being drawn by the resistive branch of the circuit. It's an Ohm's law formula. We're simply taking the given value of voltage divided by the value of resistance, which was a known value. It was 60 ohms. Plug these two values into a formula, and our current is going to be 1.87 amperes. Now, this value is already in my calculator, and I like to be efficient in my work. This is the reason why my next step, I'm going to proceed to solve for the amount of true power that the circuit, or this branch of the circuit, is going to draw. Okay, calculate the value of true power that the resistor is going to consume. We're using Ohm's law again. P is equal to E multiplied by I, or the voltage multiplied by the current value, which was just calculated, and we get, as a result, 209.07 watts. Now, I'm going to proceed to go and put this on the chart, and then we're going to move forward and start solving for the missing values of the inductive branch. We've just solved for the missing values here in the resistive branch of the circuit. I'm now going to jump out of here, and I'm going to go and start tackling the missing values in the inductive branch, specifically current draw, reactive power, and I'm going to finish up with finding for the value of inductance. So let's pack up, let's move down into another whiteboard, and let's get cracking on. Proceeding to step 3, we're going to calculate the current draw across the inductive branch using Ohm's law. We're going to take the value of applied voltage, 112 volts, because the voltage is the same at any branch in a parallel circuit, and we're going to multiply it by the value of inductive reactance. In this case, it was 85.7 ohms. Multiplying those two values together, you should be getting for an answer 1.31 amperes. Now, I'm going to move ahead, and I'm going to calculate the amount of reactive power that the inductor is going to consume. So step 4, I almost said stage 4, but step 4, we're going to calculate the amount of reactive power that is going to be consumed by the inductor using, again, it's an Ohm's law formula. We're just substituting the P with VARS L, volt amps reactive. We're going to take the value of the voltage across the branch, and we're going to multiply it by the current draw, which in this case was 112 volts, multiplied by the 1.31 amps, giving us 146.37 volt amps reactive. So this is the amount of energy that the inductor is going to consume. And at this point, what I'm going to do is to tie this up for the branch. I'm going to solve for the value of inductance. I'll have to erase this, and we're going to just keep moving on. Now, just as a little reminder, how do we go about solving for the value of inductance? This formula is given to us, and inductive reactance is result of 2 times pi times the frequency times the value of inductance. Well, we don't have the value of inductance, so we have to manipulate this formula. What we're going to do is move this down here. The formula is going to look like this. L is going to be equal to x sub L divided by 2 times pi times frequency. Well, we know that the frequency in North America is 60 hertz, and that 2 in pi are given values, and we can just put 377. So we're just going to input our value of inductive reactance. .7 ohms divided by 377. And we're going to have a value of inductance. So L is equal to 0.227 henries. Now that concludes all of the missing values that we had in the inductive branch of our circuit. I'm going to proceed to input all these values that we found, current, power, and inductance, into the chart, and then we're going to move on from there. We've got all of our values here for the inductive branch. Now let's proceed to working on this last branch, and we'll do everything for the capacitor. Here we're in step 6, starting to compute for the current draw of the capacitive branch. We're going to take the value of voltage, and we're going to divide it by the value of capacitive reactance. In this case, it was 112 volts divided by 75 ohms. And that is going to give us a current of 1.31 amps. Now, just a friendly reminder that a lot of these values have been rounded to 2 decimal places. Now, I'm going to move on to step 7, which is going to be calculating the amount of reactive power that my capacitors are going to generate. Remembering that capacitors generate reactive power, inductors absorb it. We've got the value of voltage, which was 112 volts, multiplied by the current, which we had just previously calculated, of 1.31 amps. That gave us, as a result, 156.8 volt amps reactive of power. Now, I'm going to proceed to calculate for the value of capacitance, so I'm going to be right back. We're about to get started, and when we look at our formula, we're going to input our values. Again, the frequency of our circuit is 60 hertz, and we do have a value of capacitive reactance, which was 75 ohms. So we're just going to put that into our formula. And you can't forget the reciprocal. The value of capacitance should be 35.37 microfarads. Now, this concludes the missing values that were in the capacitive branch of the circuit. I'm going to take a walk down to the other board, and I'm going to input all of those values, and then we're going to start working on the circuit as a whole. Now that I've got all three branches of the circuit completed, what remains now is to go and start solving for the remainder of, well, not the remainder, for the entire circuit. What we're going to do is I'm actually going to use a trig formula to calculate for the current draw of the entire circuit. And we're going to use that to calculate the value of impedance. So what we're going to do is I'm just going to head back down there, and we're just going to keep working through the process. We're now going to proceed to solving for the amount of current draw for the entire circuit. We're going to use a trig formula, which is a little bit different than what we've done in the past. What we're going to do is find the total amount of current, and we're going to do that by using the current draw of the resistive branch, so I R squared, plus we're going to use the current draw of the inductive branch, but we're going to subtract the current draw of the capacitive branch, remembering that capacitors basically negate the effects of an inductor. So if I go IL subtract IC, close the brackets for PEDMAS rules, square and square root. Now, let's proceed to using our actual values. 1.87 ohms squared plus 1.31 ohms, subtracting 1.49 ohms, close the brackets, squared, square root, and the current draw, or current total, is going to be 1.88 amps. So it looks like the amount of capacitance, or the current for the capacitor, is actually negating or feeding the inductor with all of its current, and the little bit that is left over, because it's trig, it doesn't add a whole lot to the overall value. Now, we're going to use the value of applied voltage and this calculated value of current, and we're going to use that to calculate the impedance of the circuit, just using straight up Ohm's law. So, here we've got the formula. It was a Ohm's law formula where we took the applied voltage for the circuit and we divided it by the current that we calculated for the circuit. Our two values, 112 volts divided by 1.88 amperes, and that gave us, as a result, 59.7 ohms. Now, I've done these calculations both ways in terms of I calculated the impedance using the trig formula, and I did it with Ohm's law. I get the same answer either way. Now that we have that, we're going to proceed to calculate for the apparent power of the circuit. Now that this is complete, I'm going to proceed to calculating for the value of apparent power for the entire circuit. Now, okay, I'm back. I've already written down what we're going to do next, and that's calculate the apparent power required by the entire circuit. So apparent power, I like the term because it means it encapsulates every type of power the circuit requires, meaning true power, or in watts, as well as the reactive power, where we're talking about volt amps reactive. So apparent power. We're going to use a trig formula, and I like this part where you can see that the reactive power being generated by the capacitor is going to negate or feed the reactive power required by the inductor. So let's start inputting the values that we've calculated into our formula. So 209.07 watts of true power squared plus, open our brackets, 146.37, subtract 156.8, close the brackets, square it up, square root, try hard to make a straight line, and so if we punch this into a calculator in a single operation, you should be getting, for an answer rounded to 2 decimal places, a VA of 209.33. As you can see, that we're only going to have about, 10.5 VA, but using that into a trig formula, it's not going to account for much, as you can see by the result, that the efficiency of this circuit is going to be really high, and I'm anxious to see this. Well, now we're at that point where we're going to calculate for the overall efficiency of the circuit, or in other words, power factor. And what I'm going to do is, once I have power factor, I normally will just jump right into angle theta. That way I'm saving myself time running back and forth from the board. I'll see you in just a couple of minutes. Determining the efficiency of the entire circuit, or in other words, power factor. Now, I've always maintained that I prefer to work with values of power as opposed to using, in this case, the current draw. And so what we're going to do is input our values. 209.07 watts divided by 209.33 VA. The results are going to be 0.998757942. Now that's what came out of my calculator, and I know that I would ordinarily have to multiply this by 100, but I don't want to do that because I would like to calculate angle theta as a single operation. All I'm going to do is I'm going to move the decimal place to the right 2 places. So I can put in my expression in as a percentage, and power factor is going to be equal to 99.8. Well, actually, if I round that, that's not 87 because this is a 5. I got to round up, so it'll be 0.88%. That's really high. Now, step 13, or our final step, which is calculate angle theta. Step 13, finding the value of angle theta, or to be more specific, or in other words, what is the phase angle difference between the voltage and current waveforms for the entire circuit if I was using an oscilloscope? We're basically taking the value of the power factor, but not the percentage, but the decimal. So the value that I had in my calculator, all I simply had to do was hit second function on a scientific calculator, hit the negative cosine, and you would have gotten for an answer 2.86 degrees, rounded to 2 decimal places. That's not a lot of phase angle difference. Now, one of the things we're also going to have to do is determine the phase angle difference. Is the voltage leading or is it lagging? Well, what we're going to do is I'm going to input these final values into the chart, and then we're going to have a look at that and figure out which way is this going. Is the voltage leading or is it lagging? So stick around and let's find out. I had mentioned that I thought the power factor was going to be very, very high, and I was very surprised, 99.88%. That's extremely good. Now, one of the things we have to figure out is what kind of phase angle difference are we dealing with here? We do have a phase angle difference of 2.86 degrees, but when I draw this out, is this a leading or lagging phase angle difference? Because this is a parallel circuit, the current waveform is the one that's either going to lead or lag the voltage. But I don't know which way to do this. So we have to go and take a look at our values. Now, I'm not sure if you can see this on camera, but the value of reactive power generated by the capacitor was 156.8, and the reactive power required by the inductor was 146. Well, the 156 basically negates and takes care of all the reactive power that the inductor was going to require, but it had a little bit left over. 10.5 VARs. Well, that means then that if I've got a little bit of reactive power left over and it came from the capacitor, I'm going to have a current that is going to lead the voltage. And it's going to lead by those 3 degrees. So in this case, I got to write down that my power factor is leading. If you're confused by this, please stay tuned to my future video where we're going to build this circuit in real life, and I'm going to look at it through the lens of an oscilloscope so I can really show you, my viewer, this voltage and current relationship, and more specifically, how power factor is directly impacted by adding capacitance into a circuit. Now, let's move on to drawing out the voltage and current relationships and talking about how does the voltage and current behave at different points in the circuit. Because the 2.86 degrees of phase angle difference, well, that only applies if I was taking a reading here at the input. But across different points in the circuit, that's not what we're going to see. We're going to see something entirely different. Now, when we start talking about voltage and current relationships at different points in the circuit, we have to remind ourselves of what is the role of that device. In the event of the resistor, we've heard on numerous occasions, and it's the popular theory, that voltage and current are consistently always in phase with one another. And indeed, I may be showing different values of amplitude, but the reason I do this is for the benefit of my viewer. I could set up an oscilloscope with different values for the graduations on the current, and I tend to go and make sure that the amplitude is not the same so that my viewer can see that there's a definite relationship there. Now, if voltage and current are in phase with one another, what does that mean? Well, it means at the point where they intersect here at this datum, or this zero line, which represents an oscilloscope, I should see that the voltage and current are actually starting at the same point. They would rise in unison, and then at this point where the sine wave is starting to decline, the magnetic field is going to start to collapse, and it is going to go back to zero and then proceed in the negative alternation. And this is what it's going to look like. We're going to rise, peak in unison, collapse in unison, cross over in unison, and continue the same trend, at least to the best of my meager drawing abilities. Now, we're also going to identify it as current by its algebraic expression, but moreover, because, well, nobody told me when I was going to become an electrician that I had to learn how to draw. I'm much better with a set of tools in my hands than a marker. So I'm going to write this out in longhand so that people can understand what it is that I'm trying to portray here. And I'll do it in red, but voltage and current are in phase with each other. And my angle theta in this case would be equal to 0 degrees. Now, we've got the resistor done. I'm going to proceed to do the same thing for the inductor. I'll be right back. Here, we're going to talk about the voltage and current relationship across the inductor. Now, inductors are known for opposing a change of current. When we have a situation such as a parallel circuit where the voltage waveform does not move or it's considered to be stationary, this is relatively easy for us because current is going to lag the voltage waveform, and the popular theory is the phase angle difference is going to be 90 degrees. So having measured this previously to turning on a camera, there's about the midway point. So this represents a half of alternation, and the midway point is 90 degrees, the midway 180, one full alternation is 360 degrees. So it becomes very easy. Now, because the current lags the voltage, I am just going to draw it here in the negative alternation, because voltage, if it's at 0 and current lags, it's going to have to be down here. So we're going to draw this out, cross where the voltage is at its peak. The current will be offset by 90 degrees, and we're going to continue this trend. Try and be accurate as I say that. And I'm going to identify it and write that down. It is lagging. And I'm also going to write that out for my viewer, that current lags the voltage by 90 degrees in a parallel circuit. It really is important that we put down those last few words, in a parallel circuit. The reader needs to have a bit of context in order to fully understand what this represents. Now, we're going to move on to the capacitor. Moving forward with the voltage and current relationship across the capacitor, what we've seen, we're still in the parallel circuit. The voltage waveform is in the same location. It's the current waveform. Now, the popular theory with capacitors is capacitors oppose a change of voltage. But in the case where we're dealing with a parallel circuit and the voltage waveform is stationary, that means that the current waveform is the one that kind of changes in relation to that. Now, if capacitors oppose a change of voltage, if I was to apply the reverse logic, that means then that the current is going to lead the voltage. And in this case, again, popular theory, the phase angle difference is going to be 90 degrees. So current is going to lead the voltage by 90 degrees. I've already taken the liberty. I've measured things out when I was drawing things. And so here's my 90 degrees. And if current is going to lead, then that means that when my voltage is at the 0, my current is going to be in the positive alternation. And so I'm going to start right about here, coming down, trying to keep that amplitude the same, at least to the best of my meager drawing abilities. And I'm going to identify this. As I tried to poke fun at myself earlier, I'm going to spell this out as well so that my viewer, or if I've drawn this out, I'm leaving some information or some context as to what are we looking at. Now, current leads the voltage 90 degrees in a parallel circuit. And again, this is leading. And there's the 90 degrees from here to here. Now, we're going to finish up, and I'm going to draw angle theta for the entire circuit. And if you may remember, it was 2.8 degrees. It was almost 3 degrees. That's going to be a little bit more challenging to draw, but I'm going to take my best shot at it. Okay, I'm already prepared. I've got this nice crisp voltage sine wave. I've reminded myself what was angle theta. It was 2.86 degrees. And this represents the entire circuit, and I identify it with Z for a symbol for impedance. Now, how do I draw this out? Well, we have to look at what was the power factor. Was it leading or was it lagging? We had a leading power factor. We actually had more inductive, volt amps reactive from the capacitor, fully negating the reactive power the inductor required, and we had a little bit left over. That translates into a leading power factor. And in this case, that means then that I'm actually going to have the current leading the voltage. So let's write that out. I've got a great memory, but it's really, really short. So this is leading. So what that means then, 3 degrees, well, that's going to be really hard to portray. All I'm going to do is basically, if it's leading, my current is going to start basically, let's say right here and over here. So current is going to basically come in here, follow the same amount of amplitude, and you'll notice I am consistently just a little bit to the left of the voltage waveform, showing that my voltage is actually leading. Pardon me, I said voltage when I meant to say current, that my current waveform is leading by that 3 degrees. I hope you found this whole process insightful. It helped deepen your understanding of the process of how voltage, current react in a circuit when we've added such components as capacitors, inductors, and how they work in conjunction with resistors. It's a really fascinating application because what we're doing is working out on paper what's going to work out in real life as it applies to things like transformers and electric motors. So follow me on YouTube and like and subscribe. I've got a video coming out where we're going to take this circuit, build it, and we're going to look at it through the eyes of an oscilloscope. So please stay tuned and keep following. Bye now.